to a lot of people, but I think we can summarize the cryptography that's used on blockchains, right? We have hashes. That's kind of a very baseline concept of having a concise representation of a piece of data. Signatures, anybody who's crafted a transaction is familiar with signatures and keys. These are kind of the, foundational sort of concepts that even that blockchains require. I put zero-knowledge proofs on here because Ethereum is increasingly focusing on focusing the roadmap towards scaling proposals that involve things like ZK EVM. Right now, though, zero-knowledge proofs are mostly on the application side. If anybody's used Tornado Cash, that's kind of the chief use case. Well, one of them. So, I mean, it's kind of obvious that smart contracts are more useful if they can do more things and if they can interact with the world at large. I think like for example, we are considering adding additional curves to the EVM SecP256R1, things like facilitating interactions with so basically being able to sign a transaction using your iPhone secure enclave and adding functionality like that to the EVM. But right now it's extremely inefficient to implement most cryptography in the EVM, and especially elliptic curve cryptography is very slow in the EVM. So how we get around that right now is we have precompiles. Precompiles are entry points from the EVM that appear as contracts from the outside but are implemented as native code. So right now, the main crypto precompiles on Ethereum are the BN128 curve precompiles. That's the curve that is like the main curve of the Ethereum execution layer right now. That's what your keys, well, no, SecP256K1 is that's what your key pairs are using for when you have Ethereum keys. BN128 is another curve that people are using for zero-knowledge applications on Ethereum. BN128 facilitates pairings. We're adding BLS 12381 curve operations in the next hard fork. This has kind of been in the works for 5 years, and people want curves with better security. And also, supposedly, this will help facilitate some new use cases because the beacon chain uses BLS as its curve. And then I already mentioned SecP256R1, used by secure enclaves on smartphones, is my understanding. Others, who knows? Unlikely, I would say. People have proposed various curves over the years, and nothing has really gained traction. But maybe I'll be proven wrong. Precompiles are actually kind of a nightmare from the developer perspective. If you don't understand the math in a very detailed way, it's really hard to assess what the hell is even going on, right? I mean, likewise, it's hard to assess what is even the usefulness. And in the past, in 2018, for example, we introduced a precompile for the Blake2 hash function that ended up being totally useless. It was useless from the start. Somebody Originally, it was purported to allow some sort of interoperability with Zcash, and then it turns out that we included a version of it that had incorrect parameters, and it made it to mainnet and doesn't do anything. Aligning the performance to the gas costs can be really hard. Recently with the BLS precompiles, we found out that there was a huge difference in the performance of certain inputs on the multiscalar mul precompiles. That may have not been found if the right person wasn't digging on random inputs that nobody will ever realistically use on, well, strange inputs. Precompiles have a large security surface. We've found countless bugs in the BLS precompiles, at least 10. These have been patched and hasn't made it to mainnet yet, and luckily we haven't had a consensus failure on mainnet due to a curve or a crypto precompile, to my knowledge. I may be wrong, but recently it hasn't happened. Precompiles can't be removed. It's just not worth the effort. Huge effort coordination to get to production. The BLS precompiles have been in the works since 2020, and they're getting there. They're shipping, but it's been an uphill battle. But so in 2020, we were experimenting with EVMMAX, which was a project to bring WebAssembly to the Ethereum execution layer. And the project itself didn't really, it didn't go to mainnet, but one of the things that we found from trying to implement various precompiles with EVMMAX was that they all elliptic curve precompiles in particular, and then actually like a lot of them, other than like hash functions are different, but like a lot of elliptic curve, some of the newfangled like post-quantum stuff, and then ZK stuff, like pairings. I mean, pairings are over elliptic curves, so they all use modular arithmetic under the hood. It's like 90% of the bottleneck. And it's one of those things that if we can optimize it in the EVM, maybe we can implement a wide array of cryptography as contracts for not that much more expensive than their native counterparts. I think a lot of people are probably, so modular arithmetic, you're taking two numbers, performing some operation, and then taking the remainder of the result. When we do operations, a lot of times we're doing them and taking the modulo of a prime number, and that's kind of like a base building block for like a lot of elliptic curve and various crypto primitives are based around modulo prime number arithmetic. So the EVM, we currently have two opcodes, addmod, molmod. They're very expensive. So these opcodes take inputs as stack parameters. They output something on the stack. The stack operations themselves are expensive. The opcodes themselves are expensive. It adds up to be about 18 gas per invocation, which is a lot. They're also just they're too general. You can pass anything in as the modulus and the values, and realistically, like in most cases, we're using values that are already reduced, that are already less than the modulus, and we're using moduli that are oftentimes, well, most all the times odd. There's not really, right? So we have these general opcodes that are just wasteful, and as a result, they're not as optimized as they could be. Yeah, so like I mentioned, in most use cases, we're using values that are less than the modulus, and the modulus is odd and prime. And in this case, yeah, we can implement modular addition and subtraction without division. Division is extremely expensive, and the current odd mod and submod require division, so they are necessarily very expensive. And then if we know that the modulus is odd, we can also remove this requirement for multiplication. And so it ends up, well, the cost of a multiplication, if we do some pre-computation on the modulus and cache a small amount of, basically cache a single number of state for a given modulus, we can do modular multiplication very, very quickly. So putting this together, we EIP 6690 is a proposal to add new modular arithmetic opcodes to the EVM. It's rather hard to summarize in a few slides, and I figured I would just give a high-level summary of what's going on, and I've kind of explained. So we the idea is that we want to facilitate improvements in elliptic curve arithmetic, but also we kind of had this curveball thrown at us where the research team in Vitalik were basically hey, we actually don't really care about elliptic curve arithmetic all that much anymore, and we want to be able to do SIMD operations on small moduli. So as a result, basically what we have are several new arithmetic opcodes, and what these opcodes will do is they will operate on vectors. And so a vector is just a list of values, right? And in this case, the values are big numbers, and they are big. So essentially, you will call an opcode set mod x. This will perform the pre-computation I talked about. It will allocate a space of memory, and then to do arithmetic operations, each invocation of add mod, submod, molmod will operate on a vector of values. So it will perform multiple operations at once. We also encode the parameters to these. Instead of using stack items, we encode them as offsets into this space we have just allocated. These aren't memory offsets or byte offsets. They are indexes to, if you think of this space as being full of big numbers, and each of these immediate data parameters is a single byte offset that references an index into a space of big numbers. So one of the implementation details of this is that by using this Montgomery trick I talked about earlier, it requires transforming the numbers we're working on into a different representation that is system dependent. Meaning that if you're using a 64-bit or 32-bit system, I mean, nobody runs 32-bit systems on mainnet, so the point is that we explicitly make this space that we operate on is not observable from EVM memory except through these new load and store opcodes that we introduce. So like I mentioned, there's this new opcode to set the active modulus, allocate a space. We also expand the range of moduli that we support operations from 3 to 768 bits. 768 was just chosen as a random ceiling to keep the implementation complexity simple. And realistically, the modular arithmetic operations above 768 bits are like RSA, and nobody's doing that on mainnet, so right, so the result is with our gas model, we have, depending on the opcode, it's 95 to 97% cheaper than the existing modular arithmetic opcodes. And it's really simple. I mean, it's a small code change, and it is straightforward once you understand it. I would say it's fairly simple to implement this as a reference implementation. Making it performant is a different story, as always. So yeah, okay, but like what we actually care about, like how well does an EVM implementation of a precompile compare to, the native version. So I implemented the BLS G1 and G2 scalar multiplication precompiles as an EVM contract. It was pretty hard because there's no tooling, so it was just like writing handwritten assembly. Had to write a templating engine for it. It was a learning experience. I couldn't implement the same algorithm that the precompile implemented because the time constraints just didn't allow me to optimize it. And so so the two important ones are the left bars here. So basically, if we take the execution time of the EVM ASM, which is Geth's interpreter, the 6690 implementation in Geth, and we take the corresponding precompile implementation in Geth, the execution time is, so right now it's about twice the runtime. And that's just purely based on execution time alone. It says gas here, but these were some old charts. I just extrapolated the execution time out to gas. If we take the costs in 6690 and compare them to the precompile costs, it's a little bit better. And I think that's mostly because the precompile is just overpriced. Ideally, well, the other thing at play too is that EVM opcodes are not, the pricing is not on par, right? So different opcodes were introduced at different times. I guess I should say, like, when they were first introduced, like, there was not really, like, it's kind of the cost model was kind of arbitrary. So stuff was not like super well thought out in 2014. I think there was like a spreadsheet or something where they just were like, yeah, okay, let's go with these numbers. And now, as it turns out, like, yeah, they're pretty overpriced. Like in this contract implementation, I think the cost of control flow operations in gas was like 60% of the overall overhead, when in the actual execution time it's like, nothing compared to the modular arithmetic. Right. I think this can be optimized though. I think that the Geth interpreter loop is, I wouldn't say it's slow, but it's not as good as it could be. There's definitely room for hand optimization there. Maybe rewrite the interpreter loop in assembly. That it sounds insane just saying that, but that might be something we actually look at in the future. Just general optimizations across the board. I think that in this case, right, and as I mentioned, like the algorithm that the contract implements isn't even the same one as the precompile. So it is a slower algorithm than the precompile. So it's really not an apples to apples comparison. But I think that, realistically, it's never going to be as good as native to execute something in an interpreter, but I think that we can get fairly close. Yeah, so that the BLS stuff I just showed you was actually implemented like 2 years ago. The proposal, it's been dependent on EOF, which is kind of tangential to the details of 6690, but like EOF gives us the ability to add new opcodes with immediates. And this depends on that. So we have to wait for EOF. So EOF is shipping the next hard fork. The Epsilon team has kind of taken over the task of spearheading the current R&D efforts on this. I know they're prototyping. So I guess something else to say is like, yeah, we're adding BLS. We're adding SEC P256R1. And beyond that, like, I don't know. There's nothing that really stands out that that people are really pushing for that will coalesce into a precompile on L1, or that makes it so that something like EVMMAX, like we need another curve, and so that this proposal will, facilitate that curve on L1. At this point, it's more about, we have all of these like ideas for, I say we, but like there's various ideas of like post-quantum gizmos and gadgets and ZK this and that, and the R&D effort is kind of shifting to that. And so the kind of common theme around what they are working on prototyping is that we're doing a lot of operations on values where the moduli is like very small, like either 64 bits or I think there was one like proving system, one scheme or that had like 32-bit moduli or something. So it kind of throws things on its head, but at the same time, we're fairly confident that like this same approach is applicable. And like another thing is that like the space of research is moving so fast, and it's like shifting around that we can't commit to a precompile. Like with BLS, we started BLS in 2020, and it's like just shipping now. We can't, if we commit to something now, we'll just find something new, and there won't, like, it'll be hard to coalesce around a precompile unless there's like some really strong effort. So a general approach where we can implement something as a smart contract, where we can implement a wide array of things in smart contracts and have them not be terrible compared to their native counterparts, I think is a decent solution for the medium term while we coalesce around a future direction. Right, so I think this will probably ship in 2 hard forks. The next hard fork, I think, is cutting it a bit close because there's still R&D that needs to happen. But it seems pretty likely that it will ship in 2026 or so. Let's see. Some resources. Radek from the Epsilon team, the new Epsilon co-lead, gave a pretty good talk about it at DevCon that dives into the actual spec a bit more. It is a bit outdated at this point because we added many things have changed. The EIP is up to date, but Vitalik wrote a blog post that really isn't entirely focused on EVMMAX, but it's more of a general like observation about I don't know if like 80-20 rules, if anybody's 80-20, like 80% of the work is done by 20% of the code. That's kind of the gist of this blog post. It's fairly interesting. And then we have monthly research calls on which you can follow along with on the PM repo. Yeah, that's what I had. So, yeah.
Thank you, Jared.
Yeah.
So now we move on to Q&A from the crowd. I think you can just put that on.
Okay. Yeah, just keep it.
First question.
Hi, Jared. So I just want, maybe could you help expand a little bit on the point that smart contracts are more useful or composable if they have access to a wide array of cryptographic primitives?
Yeah.
Like, what does it mean?
So I would say that like if you can, there is pulling like, so I mentioned like SecP256R1. There's devices that use that as their like native enclave signing curve. So if you had that in the EVM, you could cheaply verify message. You could use your iPhone as like a hardware wallet, basically. Whereas now you have to pay a lot. And I think that there's been, I guess like that comment is more about just in general, if we can implement a wider array of things performantly in the EVM. I think, for example, I know some L2s are using different curves. Like Mina protocol comes to mind, and there could be verifying a proof from a different blockchain, from a different curve. Like there's various. It is useful on Ethereum. I think like yeah. I think also if we can verify like Stark proofs come to mind. They're very expensive to verify right now. If we could reduce that by a factor of 60, 70, it just makes it cheaper and it makes the EVM more useful for L2s. So, yeah.
Cool. Like, yeah, I asked that because like also want to segue a little bit into the recent radical proposal, RISC-V, just swapping EVM to RISC-V.
Yeah.
So like I guess that's the main reason, right? Like maybe EVMMAX is a step like before we swap the whole thing over to RISC-V.
Yeah.
The question is more like, so what do you think like RISC-V will come how like in a 5 years time frame, or?
I think that I think it depends on how. To be honest, I'm not like hugely familiar with the details of that proposal, but my understanding is that it depends on like how efficient ZK EVM provers get. Like if if we don't even need RISC-V, and somehow we get like a there's some huge improvement outside of that. Because like to shift the VM to RISC-V or to change the VM at all, it's like it's the same issue that we found with WASM, is that you have to support 2 VMs, or you have to like compile EVM to RISC-V, and there's just such a, like, it just blows up the state space of stuff you have to think about as a protocol developer, where I feel like even saying, yeah, 5 years, it feels like a moonshot idea to me, where the details, like, you know, they say the devil's in the details, and I feel like this is one of those things where, yeah, I don't know.
Yeah, okay. Answers. Thanks. Anyone else?
So kind of piggying back on that. There's a Prism dev who's part of ETHKL, Nishan, who's written before, I think recently, about, I think it was more about the beam chain and how, like, you know, research is like has these grand ideas and engineering needs to actually do the work to make it happen.
Yeah.
And I think especially in recent months, like, there's all this talk about how sometimes Ethereum researchers or EF can be a bit like, you know, too much in the ivory towers and doing all this fancy research and not necessarily focusing on the actual engineering.
Mm-hmm.
And just, I don't know how much you're happy to share, but like from your point of view of someone who's part of the Geth team and also part of Epsilon before, like,
Yeah.
you probably have kind of a perspective on this that might be useful for us as outsiders to kind of just hear about.
Yeah. Yeah, I mean, I think there's, on some level, there's definitely a disconnect, and it feels like I would say it's a bit different recently. Like, so the research team is not a monolith, and I've been seeing, like, so recently the ARG team, Applied Research Group, has been like doing a lot of, they've been explicitly trying to move, I mean, it's in the name, right? Applied Research Group. They're like trying to target proposals that will actually lead to improvements, not like in a moonshot, like 5 years we go get beam chain. But I think there is a bit of a disconnect between some of these moonshot research proposals and the engineering effort required. And I wouldn't say it's because the researchers are bad or naive or anything. It just, I don't know, it feels like there's just a totally different viewpoint with the engineering side, and just the amount of complexity is kind of, they're just thinking about things on a different, in a different, totally different way. Yeah, I mean, like with the beam chain, it especially, it I don't know, it's hard. It's hard to when like as an engineer on the daily, focusing on like kind of like low level details. To I feel like there's just naturally a disconnect with people who are planning out these giant grand things, where the time of my time on the daily, I you know, I'm solving bugs, or I'm like trying to figure out why something is slow, or triaging issues, and I think there's just like naturally this disconnect and void between the researchers and people concentrating on the daily grind of things. I'm like trying to be diplomatic about it, you know, but
on this EVMMAX, so basically it's focusing on modulus operations.
yeah.
Other than the ZK stuff, is there any other uses of having modulus operations?
Yeah. So there's various I don't even know if you'd call them ZK schemes. There's various like proving schemes that post quantum I guess you would call them ZK though, actually. So
essentially
no, yeah, I'd say
stuff.
it mostly coalesces around ZK and like proving execution and schemes that are trying to look post quantum. And I mean, there's this like fear that with the advent of quantum computers, everything's going to suddenly break. So I think they're really focusing on, I think I had a slide about Falcon signatures. That's like the new hot stuff is Falcon signatures. And the thing is, like, under the hood, like, it's all bottlenecked by modular arithmetic. So, which is good for this proposal. So, yeah. But to answer your question, honestly, yeah. I mean, I think it's like all ZK at this point.
But I mean, ZK itself is a huge unlock for many things, right? So,
Yeah.
do you know of any L2s or even L1s who are kind of interested to implement this, maybe before Ethereum?
I don't think so before Ethereum. I think this is still like pretty deep in the R&D phase. And for so long we were concerned about like implementing elliptic curve stuff with this, and then it changed to, we need everything, and we don't care about elliptic curves. So, but I think there's been promising results, especially with Falcon signatures. I know like Radek I think he implemented them recently, and it was like, only costs like 5,000 gas or something, which is like pretty decent. Like, I think verifying a SecP, like verifying an Ethereum signature costs like, I forget if it's like 2,000 gas. They might have lowered it to like 500, but it was 2,000 gas for a while. So if we can write a contract that verifies a post-quantum signature in 5,000 gas, like, I'll be happy. So, yeah.
Thanks, Jared. This was really insightful. So
Thank you.
I think that the sound of this EIP itself is very interesting, but I think it touches a lot more on the client side, or at least like the protocol side that we've been hearing a lot on. So I'm curious more from the application side now. So for like application developers, I'm curious what this unlocks when this is live, and then also a bit of we touched on how it scales cryptography. So what about the hashing functions that are existing right now in our opcodes, for example, like Kachak 256? Like, how does this affect all of these cryptographic opcodes? Would love your thoughts on that.
Mm-hmm. But did you ask about Kachak 256? Did I hear you say that?
Yeah.
Okay.
It might be a bit of an elementary question, but we'd love your insight on that.
No. So like for that one specifically, and a lot of hash functions, this actually has no application. And the reason is that like Kachak and many hash functions are like bit shifting. It's all bit shifting under the hood. What this does unlock, so I'll give a specific example. Tornado Cache, let's just say mixers. It's kind of keep it legal here.
It's fine. You won't be in trouble here.
Okay. So this unlocks a for that specific application. This unlocks a I think it was like a 40% cost reduction. So you're going from I mean, I don't even know. I don't know what that is currently in currency, but you're going from. It's substantial. It's substantial, at least $15. I'm just pulling that, ballparking that. So with this proposal, verifying a SEC P256R1 signature goes from, I think it was $50 to $5. Now the precompile is 50 cents, but it's kind of a catch-all. The unlock is sort of anything. If you want something that there isn't enough effort to push forward a precompile around, this will give you a 10x cost reduction or 90% cost reduction versus implementing it in the EVM now. And I think that if you can efficiently, like, so we have these like random new proving systems coming out, and if this enables people to experiment and take their research paper and actually implement it in a way that is affordable versus now, I think that's a good unlock for people being able to innovate on Ethereum. We were really hoping that the BLS precompiles wouldn't go in, so that this would be like, the huge unlock is that we beat the BLS precompiles, but can't win every battle. So, yeah, that's my the answer I'll give to your question.
That was helpful. Thank you.
Yeah.
Hello, Jared. So I understand that the EIP, was it 6699? Yeah, whatever that is. So
Yeah, 6690.
yeah. So I understand that essentially the opcode that's being introduced helps with optimizing modular arithmetic, right? And then I also understand that the roadmap essentially would basically have solidity support for the opcodes as well, right? Eventually,
Yeah.
I think that's what I saw somewhere. So I also understand that the current focus, it's BLS curves and SECP R curves.
Yeah.
So does that mean that once you have support for solidity, once we get to that point, does that allow anyone to just go on to solidity and write assembly codes and essentially come up with their implementation for whatever curve that they wanted to bring to the EVM? Like, is that a focus for EVMMAX? I'm just curious.
Yeah, totally. So, I mean, you could make the argument that they could do it now, but it's just really expensive. Like, you could even make the argument that you could implement BLS in, well, I don't know about Solidity. You could definitely implement, you could implement it in Solidity because you can write assembly in Solidity, but it would be so expensive. It would be ridiculously expensive. So, yeah, I forget
So
exactly what your question was.
Yeah, so I'm just kind of like curious about, like, once you have that opcode brought into the EVM mainnet, like, does that help reduce the gas cost by, I don't know, instead of 1 million gas to like 100,000 or even 10,000?
Yeah, yeah,
That's
definitely.
still pretty reasonable.
Yeah. I'm sure there's like actual use cases for curves that aren't SecP 256R1 and BLS right now, but it's like, I guess like people on the research team that I've talked to seem to think that, oh well, you know, we don't need any more curves because we can just prove this in a snark. We can prove any curve in a snark, and it's I guess it just kind of rings a bell for the disconnect, because like, yeah, sure, you can prove any curve in a snark, but like the prover cost could potentially be insane. Yeah.
I kind of like that you brought up Snark, because we're going back into, because it reminds me of ZK VMs, and then we're gonna go back into RISC-V at that point.
Yeah.
So we're essentially going back into the argument that whether if we're gonna go with RISC-V or if we're gonna go with opcodes, I guess. I don't know. I'm just.
I honestly don't know that much about RISC-V, and I did read that thread, and it sounds like a lot of people who are more in the know about ZK VMs have strong opinions and potentially conflicting strong opinions, and yeah, I mean, I will follow that proposal as much as I can, but I'm not writing a ZK VM, so not the guy to ask, but
Yeah, I'm gonna open up to other people. Yep.
One easy one to let you
okay.
off. Just like so you mentioned, like, you know, for your work you have to do assembly code and so on. If there was anyone here who's potentially interested to join the Geth team or client teams in general, like what would be your advice? Like how would it be different versus becoming an app developer, for example, or even a researcher?
I think if you're interested in joining a client team, it's not necessarily going to be, I mean, I know like on the Geth team we're not hiring, so the bar will be very high. You'd have to be some kind of, you know, savant for them to be like, yeah, okay, we'll open up a space. But I think in general, just going on the GitHub and trying to be helpful and being respectful of people's time and not expecting them to babysit, and then just like picking up issues and really learning the code and learning the semantics of how the weird parts work. Yeah, I mean, that's kind of a general response, but like that is the best catch-all advice I would give if somebody wants to become a client developer, is to just start picking up issues and pull requests. And
Should you need to know how to do like low-level coding?
assembly, no. Well, I mean,
Doesn't hurt.
maybe if you want, it's if you already know assembly and you can come in and be like, yeah, I can optimize your Ketchuk implementation in you know, for this platform that like one user uses, and they're like, wow, that's so cool, like maybe that could be your angle in. But like in general, yeah.
You don't really need it for your day-to-day.
Hmm?
You don't need it for your day-to-day kind of work.
No. yeah, just get good at triaging issues. I mean, cool.
Let's have a group photo. Vice, where should we stand?
So I didn't mean to put you on the spot. with
No,
that
it's
question.
fine. It's fine.
It's recorded right away, so it was a good diplomatic answer.
Delete the part about the research team, but oh, it's sitting. Okay.